Rada s vami, Sivonia. No, ja nie mogę czytać doklad po-ruski, извините меня, будет по-английски. So, the general topic of the lectures which I gave are connections in characteristic 0, in characteristic P. So, это лучше here. So, I'm not going to give a course on connections. Rather, I would like to present some deep problems which are coming from the definition. So maybe we start first with the definition, and then I will discuss a few problems, and today we just present a program here. And in the second lecture and in the third lecture, I will try to highlight a few points of this program here. But let us first start with the definition. So, definition. Let X be a manifold and in fact, there are many ways to think of a manifold. The first one could be a C-infinity manifold. It could also be a complex analytic manifold. So I abbreviate manifold by MFD. And mostly for us, it will be an algebraic manifold. And mostly we will never talk on C-infinity manifolds. So when we have a manifold, we have a sheaf of one forms, which we just saw on Riemann surfaces in the previous lectures. So let omega 1 be the sheaf of one forms. So for example, if we were dealing with a C-infinity manifold, it would be the sheaf of C-infinity one forms. If we are dealing with a complete analytic manifold, then that's the sheaf of complex analytic one forms. And if we are dealing with an algebraic manifold, that's the sheaf of algebraic one forms. So for example, as we saw in the previous lecture, if X is a Riemann surface, so complex analytic manifold, then it has local parameters Z, and then locally, the sheaf of one form here, this is just O dz with the standard rules, where O is a sheaf of holomorphic functions. And then when we, so I don't like too much complex analytic manifold. I'm really doing algebraic geometry. So I just replace the Riemann surface by a smooth algebraic curve, Z by a local parameter. Earlier on, local meant analytically local. Now it means Zariski local. And O is no longer the sheaf of holomorphic functions, that's the sheaf of algebraic regular functions. And then we have a notion of a coherent sheaf. So E is a coherent sheaf. And in fact, it can be a vector bundle, so locally free. But in fact, it's not really a requirement. It's going to be a consequence of the definitions here. And we had an example earlier on. The locally free shifts Dimitri was considering was a Frank 1, and this was a linear system. And a connection on E. So this is a connection on E. This is just here. This is a map here, which is a map of abelian sheaf. But it's more than this. It fulfills, it's not really all linear. It fulfills the so-called Leibniz relation. Which says that, which measures precisely the defect to all linearity. And it says that, so a coherent sheaf, it's an O module, it's a sheaf of O modules. So O acts on E, and then the nabla, the Leibniz relation is a defect to O linearity. So if E is a local section of E and F is a local section of O, then nabla of F times E, this is dF E plus F nabla of E. And we have a notion of a curvature. So I just give an elementary definition, but then we will higher up the viewpoint on what we are doing. The curvature here is we iterate nabla. So we continue here. Again, we write nabla and we make precise what we say here. So we define nabla of omega tensor E, where omega now is a one form, and E is in E, with a sign convention, which is this, minus omega nabla E. And then one computes that nabla square here, so nabla post-compose with nabla, which I just abbreviate by nabla square, which is called the curvature, has the basic properties that it becomes all linear. And this is called the curvature and integrality or flatness. Flatness of nabla, or sometimes one says integrality, is precisely saying that the curvature is zero. Okay, so then we have, I need at least that much to present a program here. So we are just considering the category of flat connections. So I erase the board here. So we come to this in a minute. But before coming to this, I have to present a few very tiny little definitions. So because of the integrality, so we consider the category of flat connections. And one very important, so you have seen that the flatness enables us to post-compose the connection by itself, going from a sheaf to the sheaf tensor omega 1, and then from omega 1 tensor the sheaf to omega 2 tensor the sheaf, and so on. So this yields a Durham complex. So this flatness here yields a complex omega 1 tensor E, omega 2 tensor E, omega 3 tensor E, and so forth, where the sign rule on omega tensor E, where now omega is an n form, is d omega tensor E plus minus 1 to the n omega nabla of E. So this theorem complex here, by the fundamental theorem of point carré in complex geometry, or at least we call it the point carré lemma, on a complex, so I abbreviate complex by CPLX on a complex manifold, is telling us that this complex, which is called the Ram complex, this Ram complex is exact. So let me abbreviate the Ram complex by DR. So the Ram complex is exact on a complex manifold. And if now we are doing algebraic geometry, if X was an algebraic manifold over the field of complex numbers, then the Ram complex is still exact if we think of the algebraic manifold as an analytic manifold. So if we consider XAN, which is the underlying analytic manifold to the algebraic manifold, or if you like, that's the complex manifold which one obtains was by considering the complex points of the algebraic manifolds, then the Ram complex is exact everywhere except in degree 0. And then in degree 0, the kernel of the connection here, this is a local system. So ker, so E above nabla, which is the kernel of nabla, from nabla to omega 1 tensor E, then this is a local system. Which means it is locally trivial, i.e., it's locally trivial in the complex topology, I mean in the analytic topology. And because it is locally trivial, it yields if we fix a point. So let dot be a point of our complex manifold. Then we have an action of the topological fundamental group. So let me write by pi 1 top x base at this point on the fiber of the sheaf at this point, on E, the fiber of the sheaf at this point. And this action is like this. So we are looking here, we have a point here. Now we are looking at the topological fundamental groups. That means we are looking at homotopic classes of loops which are centered at this point. And now we have the value of the sheaf here at this point. And the value of the sheaf here is just a section of this vector bundles here. And we look at loops like this, and we are looking at the kernel of the connections. That means we are looking at solutions of this equation here. And as we move here, because the sheaf is locally free here, we start with local disk here. It's locally free in the strong topology. So on each such disk, the sheaf can be trivialized. So we do like this, we trivialize, and then when we come back, we have a new value of the section here. So we assign to gamma in pi 1 top, and a section E in EX, we assign gamma E, which is a new value here, a new local section. So this yields a linear, this is a representation from pi 1 top x dot to the linear group on EX. I forgot to say here EX is a fiber of the sheaf at the complex point EX, so this is a complex vector space. Of dimension, which is precisely the rank of the sheaf. And this is called the monodromy representation. And then the 19th century Riemann-Hilbert correspondence. So I have to come to the category of flat connections. We are not yet there. I have to mention the Riemann-Hilbert correspondence, and then I can present a certain program. Pardon me? Excuse me. Hello? Hello? You are louder than me, so I cannot hear him. Yeah. I apologize. Also fiber of what? That's the same thing. So this is a very good question. Thank you for the question. You are completely right, and this is the same thing. Thank you very much. Okay? In fact, when we'll say what is the category here, we will see. So thank you very much. So let me write the Riemann-Hilbert correspondence. And in fact, that this is the same thing is the theorem of Sofia Kovalevskaya. So the theorem of Sofia Kovalevskaya is going to tell us that if the bundle has rank R, there are R linear different, there are R linearly independent solutions. Yeah. And it's given by initial conditions, and this is precisely the vector space you are talking about. So you have a question?
Yeah, now we have a
question. Please.
Just about the definition of phi1 representation.
Is that okay now? Yeah, okay. But it's better you ask the question, because otherwise I cannot cover your voice. So okay. So the Riemann-Hilbert correspondence is telling us this. So in fact, I insist, I'm really glad to answer your question, because the fact that the rank is, the vector space is the same is precisely the theorem of Sofia Kovalevskaya. So the Riemann-Hilbert correspondence is telling us that if we consider the category of flat connections, so that's the Riemann-Hilbert correspondence, let's say, of the beginning of the 20th century or end of the 19th century. So the category of flat connections on X analytic manifold is equivalent to the category of a local system, and let us write immediately to the category of equivalence classes of linear representation of the topological fundamental group. So here I should put a dot here for any rank modulo conjugacy. And this correspondence here has been enhanced. So here, this is in the analytic category. Now, if we do the same thing on X, algebraic complex manifold, then this equivalence of category has been enhanced by the linear. And if we want on the right-hand side to have the same thing as here, but where we here replace the algebraic manifold by its complex points here, which I had denoted by X upper N here, N for analytic, then on the left-hand side, you are forced to put some conditions at infinity, which I'm not going to spell out in details because it is going to be irrelevant for long discussion in the 3 lectures. Here you have to put regular singular. And if there is some necessity, I'm going to explain more in details, but you just take it as a black box here. That, this equivalence of category can be phrased in the algebraic category. If X is not proper, one has to put some gross condition at infinity. So this is one thing, and now I come to your question before presenting part of a program here. So now you may raise a question, which your colleague just did. Give us examples. So, examples. The most important examples are the following one. And you will see, because they are the most important ones, in fact, they are basically the only connections which we really know somehow. The deepest questions which are attached to this definition here are of arithmetic natures. So we leave the world of complex geometry and we enter really algebraic geometry and arithmetic geometry, and they are related to the connections I'm going to write on the board here. So one way to produce a connection, a simple way, is to say the following thing. We have our X, and let me assume now we will do algebraic geometry, so let us assume X is an algebraic manifold, but over the field of complex numbers. To start with, we take X, and then we know that if we take the topological fundamental group, then we know that by the very definition of the topology, or one possible very definition of the topological fundamental group, this is precisely the isomorphism of the fiber functor of topological coverings, which is given by these base points. This means that when you look at any, so we look at the underlying analytical manifold. So this topological fundamental group exists only on topological manifolds. So that means we are looking at the underlying topological manifolds here. And here we look at covers in the sense of Riemann and Poincaré. And then when we fix the base point here, so let's say pi, so for any such pi, we can assign pi inverse of x. And this is a functor from the category of covers. So the covers means here unramified covers, to the category of sets. And the miracle of the theory of Riemann and Poincaré is precisely that the topological fundamental, so we can look at the, this is a functor, let's say psi. We can look at the automorphism of psi of this functor, and this is precisely the topological fundamental group, which says, I mean, it doesn't say, but there's a second part of the theory which is telling us that any representation in the category of sets of this group here is precisely a cover, an unramified cover. So it's a sort of Tanaka duality which predates the Tanaka theory. And the example here is coming from the following fact, because we want to stay in the algebraic category. We can look at this topological fundamental group, which, by the way, is an abstract group. But one shows that it's an abstract group, but it has a very strong property, namely it is finitely generated. And the first relations are also finitely generated. This is usually abbreviated by the terminology, it is finitely presented. So we can look here at its pro-finite completion. So according to what we say, a representation of the pro-finite completion, which is going, so because it's pro-finite, it is endowed with a topology, which is a pro-finite topology. And then a continuous representation here of this pro-finite completion in a finite set is the same as a representation of the topological fundamental group with values in this finite set. And according to what I said here before, this corresponds here, I should say automorphism of a finite set, I apologize. This corresponds precisely here to unramified, but now finite cover of the underlying analytic manifold. And the Riemann existence theorem tells us something extremely profound, which is not absolutely difficult to prove, but still it is profound, is that Y itself is algebraic. X is algebraic, so is Y. So this led Grothendieck to define independently this pro-finite completion of the topological fundamental group here, and this is called the étale fundamental group of X. And this exists regardless of the fact regardless of whether or not X is defined over the field of complex numbers. So in general, we have the definition. So for any X, and now let me write a scheme which has to be connected. And we will do schemes of finite type. We fix a geometric point so this plays the role of our dot before, and one defines, or Grothendieck defines, the étale fundamental group based at X, which has a property that it is equal to the pro-finite completion of the topological fundamental group here, of the underlying analytic manifold if X is smooth, if X is a manifold over C. So now I come back to what I said before. So we consider, so that means this unramified finite cover here, in fact, by the discussion we have here, we can erase analytic here, and it's better to replace the unramified finite, which is the same thing, with étal finite. So now if we have, I repeat the upshot of the discussion here, if we have a manifold, an algebraic manifold here, we have a finite étal cover. Let me denote it by H here. And then we have a connection which is constructed like this. So this is flat connections, which is defined on X, which is defined like this. We consider just a trivial connection. So I forgot to say that we have a trivial connection, OD. It's called the trivial connection. And what is a trivial connection? O is the sheaf of regular functions. And then we have the Kähler derivative, Kähler derivative on the sheaf of regular functions. So we apply this to Y. And then we know when H is étal finite, the sheaf of one forms here comes from downstairs. So this is H upper star of the sheaf of one forms on X. And consequently, we can take the push down here in the following way, applying projection formula. So we obtain H lower star of Y, which maps via H lower star of D to H lower star of H upper star of omega 1 X, which is omega 1 X tensor H upper star of Y, tensor over OX. And this is a connection, a flat connection. And now any summand of this one in fact here, because we are in characteristic 0, this is semi-simple, so this connection is a sum of irreducible connections, and any summand of it is first example is any summand of it has a high interest and it is trivialized by this, so it trivializes, so any summand of it, let me call it inabla, has a property that H upper star of inabla is trivial. So I didn't define what is a pullback connection via morphism, but it's an obvious definition. And this is equivalent to saying that the monodromy of inabla is finite. So this is equivalent to saying that the monodromy of inabla, which we defined before, that means the monodromy was the image of pi 1, in case we are over C, of pi 1 top X analytic, based at the point we want, into GL, I mean the linear automorphism of E restricted at the point. So the image is finite, it's called the monodromy. And in fact here, we see immediately, so this is the first example, and this connection here is a particular case of a Gauss-Manning connection, which I'm going to explain immediately. But here we see that, so let me first write here, this is a particular case of a so-called Gauss-Manin connection. So Gauss, Manin are what in Russian? Manin connection, which I'm going to write, I'm going to explain immediately. And it consists of, this is a particular case, and this is precisely the inabla with finite monodromy. If I am over C. But if I am not over C, I cannot use this word finite monodromy, at least not the way I present it, but there is a way, and it's worth to write it on the board because it relies on your question here. It's because of the Riemann-Hilbert correspondence. So this equivalence of category, so the Riemann-Hilbert, so this stands for Riemann-Hilbert. Correspondence was equating a category of integrable connection with a category of representation of the fundamental group up to conjugacy. But in fact, this correspondence, there is one thing I didn't say, is that it is a tensor correspondence. And now I don't want to enter into the details, but both categories are Tannakian. So that means they are linear. So both categories are linear over C, because here we were talking over C. They are abelian. They are rigid. They are monoidal. So there is one way to shorten this whole discussion here, because here we have a fiber functor and I don't enter into the details here, is to say that they are Tannakian categories. And then the equivalence of category between those two here is a Tannakian equivalence. Consequently, when we look at inabla here, we can also say it's another way of saying, so we can compare the Tannakian group on one side and on the other side. The Tannakian group on the side of connections is the Zariski closure of the monodromy representation on the topological side here. So consequently, to say that inabla has finite monodromy, in fact, has a meaning. So we can also talk on monodromy on any X manifold over a field for which the category is Tannakian. And now comes the first word in our title here, characteristic 0. So we can say that we can talk on monodromy on any X manifold over a field. So when I mean manifold over fields here, I should be more precise. I should say smooth scheme of finite type. Okay, this is what I mean here. Over a field, let's say K, over which the category of integrable connection is Tannakian. Connections is Tannakian. And those are precisely the characteristic 0 field. And we will see that later. So I started 11:30, so it's good. So today or tomorrow, we will see. And those are precisely the characteristic zero field. Okay, so we have a purely algebraic way.
Would you please read this?
Yes, so we can also talk on monodromy on any scheme of finite type which is smooth over a field over which the category of flat connections is Tannakian. And then I tell you, I don't justify it yet, it will come later. Those fields for which the category of integrable connections or flat connections over any scheme of finite type over a field is Tannakian are precisely the characteristic zero fields. So we can talk here on monodromy, finite monodromy. We don't need, we can use this terminology over any characteristic zero field. But we also saw that finite monodromy here, the way we define it is precisely, so another way of saying, so yet another way, yet another formulation. The finite monodromy connection, so is with finite monodromy, if and only if there is y to x h which is finite étal, such that H opposed star of the connection is trivial. Trivial means trivializable, and trivializable means, i.e., H opposed star of I nabla, it's isomorphic as a connection to a direct sum from 1 to the rank R of the trivial connection. Okay, so, and notice before, even though we don't talk on this right now, note this last definition is meaningful in characteristic P. Is meaningful in characteristic P. Okay. So yet another formulation of the same thing. I nabla is with or has finite monodromy. By the definition we gave, if and only if, we gave it differently. We were constructing first a finite étal cover, then we took a summand of the push-down connection, and now I say one step further, then has finite monodromy if we were over the complex numbers, or in general over a characteristic zero field with this more formal definition, if and only if there is a finite étal cover such that the pullback connection is trivial. So this gives a big category, which is controlled by the étal fundamental group, and this answers partly the question, and now I'm going to embed those connections here in a larger category, and this is the Gauss-Manin connections here. So let me explain this. I said those connections with finite monodromy, it's a particular case of a more general construction which is due to Gauss-Manin and which says the following. We consider H from Y to X, and now it's no longer finite étal, because finite means proper, étal means relative dimension 0. N smooth. So now what we do is the same thing, but in higher dimension. So we assume H from X to Y is smooth. And let's say projective. We could say proper, but let us make it easy. Let us write projective. Then we can assign to it, we fix a number, so let's say N, a natural number, which could be 0. And we consider first the relative Durham complex for the trivial connection on Y. And this relative Durham complex here is obtained as a Durham complex. Recall, we had defined the Durham complex, which was OY, omega 1 Y, omega 2 Y. So this was on the trivial connection. And now this one maps to the so-called relative Durham complex. That means we post-compose with surjection from differential forms, here relative to the ground field, to differential forms relative to X. So it maps to OY, so let's say relative to X, omega 1 Y to X, D relative to X, I apologize here, omega 2 Y to X, and so forth. So this is just for getting, just looking at the relative situation. So notice here, so for example, if H is étal, then by what I said before, this relative Durham complex is in fact the same as the Durham complex. And then we, except that I wrote it in the, I made a mistake here, I apologize. So I say that later, I apologize for this. So then what we can do, we can consider, oops, I apologize, the relative cohomology of this Durham complex, and one compute, it's a computation due to Katz, notably, but also Gauss, I mean, one says Gauss-Manin, but in fact it's written in Katz' seminal article, and it's written partly in Manin's article, trying to prove the Mordell conjecture in the function field case, introducing the Gauss-Manin connection, so Manin introduced it. So it maps here to omega 1 X tensor over OX Rn F lower star omega dot Y over X. And this is precisely, this is called the Gauss-Manin connection. This is a connection, it's integrable, and it's called the Gauss-Manin connection. Let me just show you how it works here. Yes?
Which paper is this and which picture is different?
Well, the paper, I think, when you look at the program, it is written, yeah, for cats. So let me show you how it is constructed here. So, for example, let us take n equals 0. So we are just looking at H lower star. And we want to map it like this. And that is easy because what you have here, it comes from the following. You have here the relative Durham complex. And here, and let me assume for simplicity, except that it goes like this. Let me assume for simplicity of the lecture here, so assume X has dimension 1, just for simplicity. Then this complex here receives the absolute complex. And so forth. And it's easy to compute the kernel. So the kernel here, we look from absolute form to relative form. So this is just H upper star of omega 1x. And here we look at two forms mapping to relative two forms. And because the base has dimension 1, this is H upper star of omega 1x tensor omega 1 y over x. And here the next one here, which I haven't written, would be H upper star of omega 1x tensor omega 2 and so forth. So the Gauss-Manin connection here, so for example, let us take H upper star. So H upper star are sections, H lower star, excuse me, are section of H lower star of O, that means O on X. I assume the fibers are connected here. So I forgot to say we can, well, no, I don't have to assume this. So we are looking at sections of H lower star of Y. And we want them, so it's a cohomology class here in the complex. So we are looking at sections of H lower star of Y which die here. So let's say S here with D, so relative to X, with D relative to X of S is 0. But if it goes to 0 here, it means when I derivate here, it lands here. And then one computes that because it goes to 0 here, this section we obtain here goes to 0 here, and this is precisely the Gauss-Manin connection. And more generally, what one says is that when we take the relative cohomology of this complex here, we have an exact sequence of complexes. We take the relative cohomology of the complex on the right, and then we look at the connecting homomorphism. The connecting homomorphism gives a class, a relative cohomology class on the left-hand side, and via projection formula here, a relative cohomology class here is precisely a cohomology class here. So the Gauss-Manin connection here is precisely the connecting homomorphism which is on the right board. And this is here, if you take, so note, if you take H finite, then what did you write on the right here? So if we assume H finite and smooth, this means étale, then we have that those relative one forms are 0. This is 0, so we obtain here. And what we do here is precisely what we did before. Okay, so that means our finite connections with finite monodromy are a particular case of Gauss-Manin connections, and we define here with a definition let X be a smooth scheme of finite type over a characteristic zero field. Let's say K, then a connection is of geometric origin, is said to be of geometric origin if there is an open, a dense open, such that we restrict our connection, so connection, I forgot to say, I apologize, inabla, such that when we restrict the connection to this open, then it is a subquotient It's a subquotient of a Gauss-Manin connection as we defined before. It's a subquotient of a Gauss-Manin connection. That means coming from a relative cohomology of a smooth projective variety. Okay, so a big question, because those are the connections, flat connections, which are coming from geometry, we say of geometric origin. A big question, a deep question, is how to recognize those connections, how to characterize them. Yeah, we come to this, but let me pose this as a, so let's say it is 12:30. I want to present you one question more precisely, and what you refer to is the theory of Simpson, which is part of our discussion. So I don't know exactly. Okay, let me make a break and pose you a nice question, which is going to be related to the deep conjecture which is behind here. Let us come back. Pardon me?
I just wanted to ask you to give the definition of Gauss-Manin. Never mind.
Never mind. Okay. Never mind, because we do, at least for Manin, we do 100 years earlier now. We go back to Kronecker. Okay? So one of the many theorems of Kronecker is the following one. And this is related to this deep question here. We don't deviate from our program. I just want to show you one motivation, and in fact there is a question behind which is unsolved, or meta question which is unsolved. So we go back to Kronecker here. And we take a complex number, let's say A. And we will think of A as being monodromy, and I will explain to you later on how. But, so let me say monodromy here. And our question is, I will justify this, it's just a word here. Our question is, give me a characterization for A to be a root of unity. So if you like, mu infinity of C, a root of unity. And I want to say if and only if something, okay? Now you think with me, because I believe you know that. One characterization of A being a root of unity. Of course, if A is a root of unity, clearly it is an algebraic number. Okay? So on the right-hand side, we need the condition algebraic number. Okay? But in fact, it's more, because if it is a root of unity, it's not any algebraic number. What is a minimal polynomial of a root of unity is something like x to the power n minus 1. So that equals 0. That means the coefficients are not only in Q, the monic polynomial, which annihilates the number, here's the complex number, does not have only coefficient in Q, but also in Z. So in fact here, we can start saying if and only if it is an algebraic integer, okay? So let me write A lies in Z bar, so this means algebraic integer. But it's not enough. What is the next condition? Yes, very good. But module just for A? This is brilliant. So that means we make a little diagram here, a little picture, and then the second condition is that all the conjugates of A, so let me write A sigma here, have complex norm 1. Okay? And this is, so I don't do the proof. You can talk among yourself. It's a classical proof. It's very beautiful. So this means not only A, but all of the complex conjugates here have norm 1. Is that okay? So this is a characterization, this one characterization for A being a root of unity. Now let us together give a second characterization, and the second characterization, in fact, both characterizations are related to this deep question here. I will explain how. But first, let us do number theory. Elementary but beautiful number theory, okay? So clearly, A is a root of unity if and only if, and this is not a deep theorem, if I write A equals exponential 2 pi square root of minus 1 times B, where B is in C, then I don't do anything here. A is a root of unity. If and only if what for B? Yeah, B is in Q. Is that okay? I mean, here I don't consider that as being a theorem. I mean, we just translate the problem. So I had said without justification here, A is on the side of monodromy, and here I say without justification, it comes later, B is on the side of connection. I will justify later. Okay, but now focus. So let us give a criterion, B lies in Q, if and only if what? That is more subtle than the first one. So, by the way, there's one thing I forgot to say, and you will agree with me, that this characterization here is an analytic characterization. Well, let's say it's an arithmetic characterization because we are talking on algebraic integers, so this is really number theory, but we use a complex norm. A complex norm is an analytic invariant. It's not an algebraic invariant. Is that okay? So let us say it's analytic, because everything is arithmetic, so let us say it's analytic. It's arithmetic and analytic. And now what I want here is something which is arithmetic and geometric. But in fact, it's purely arithmetic on the other side. So give me an if and only if condition, necessary sufficient condition, for a number B, which is a complex number, to be in Q. So clearly, if we want B to be in Q, it has to be an algebraic number, clearly. So that's going to be condition number 1. So let us write it. Okay? So Q bar, that means algebraic. Okay? So that means B is in a number field by definition. Okay? So let me write here, i.e., is not enough. So here we had, if you like, 1 and 2, and here we will also produce 1 and 2. So we are by 1 here. Okay? So to say that B is in Q bar is to say B is in a number field, so let us write number field. So let's say B lies in capital K, where capital K is a number field. Okay? But this is not enough. So if a number, and by the way, we don't want, of course, B to be an algebraic integer. Huh? This is not, the question is in Q. So we have to stop here. But we have to say something more, which is what? To say that an algebraic number, that means an algebraic number, is in Q, is to say that in fact it is in the prime field of the algebraic field, of the number field, okay? Because we are in characteristic 0. And now I will do really arithmetic. Arithmetic in the sense of arithmetic geometry. And this is, of course, what we love. And what is that? If B is in capital K, it means it has, by the fundamental theorem of Dedekind, of the ideals in a Dedekind ring, when we look at the number ring in our number field, any ideal, okay, is a product of prime ideals affected with some coefficients. So that means when I localize outside of those finitely many prime ideals, this B here can be reduced modulo the prime ideal. Do you agree? So this means, so this is equivalent to saying, and let me use a classical notation, that B lies in the number ring, but localize some finite set of primes here. Or let me write sigma here. It's a finite set of primes. Is that okay? Note, I haven't said anything new. Huh? To say this is equivalent to this is equivalent to this. Now comes the condition.
Maybe it's for any prime ideal, it should be prime Q.
This is perfect. So, which is not in the bad locus. Yes. But in fact, so this is precisely this. So for any P, let me write P like this. It's beautiful German P. For any P which is not in sigma, then we can look at B mod the prime ideal. So B mod the prime ideal, by the very definition, lies in the residue field. So this lies in O K sigma divided by P, which is a finite field by definition, or by elementary number theory. So it's a finite field. So usually, so this is called the residue field of the prime ideal. So it has characteristic P, P being this guy, P positive from our title. And so the prime field here is FP. And the condition is precisely this. So those two characters, so let me call this characterization here the arithmetic characterization. This one is the analytic characterization. Oh, I just write analytic here, and let me call this arithmetic. And arithmetic for me, and in fact for all the lectures which are going to come, is precisely how to add. You see what we have done before I further comment. What we have done is we want to understand when a number in characteristic 0, a complex number, is a root of unity, and we end up with a characterization which is a characterization by the mod P reduction of this number. Okay? This is precisely the theme of our lecture. So now, let me show you here. So first, let me pose you a challenge, a little challenge, before we continue. What time is it? So we still have like 20 minutes, right? So I'm not sure I come to Simpson today, but if not today, tomorrow. Okay, so I say this was clear, and you can ask your colleague. And here is maybe less clear, is that B is in Q, or equivalently A is the root of unity, if and only if B is an algebraic number, and mod P in fact, I said for all P not in sigma, but in fact, I could equally say for all P not in a finite set of primes containing sigma. So let me write sigma prime containing sigma, but of course, yes, of course. What we want is that this sigma prime be finite here. And the terminology for this is to say for almost all. There is even a mathematical notation, usually one says 2. So this means for almost all P. Then B mod P, the reduction mod P, which is in the residue field of the prime ideal here, has to be in the prime field. That's the characterization. So now, is that okay? Can I go on? Now let me pose you a little challenge, a little one, but in fact I cannot solve it. If we could solve it, this would be, it's a challenge, but it's a sort of meta challenge, because it's not an extremely precise question. Are you here with me? So the condition 1 and 2 on the analytic side is equivalent to the condition 1 and 2 on the arithmetic side. Do you agree? Because this is how we constructed the boards here. We said A is a root of unity, this is equivalent to 1 and 2, and B is in Q, it's equivalent to 1 and 2, and A is a root of unity if and only if B is in Q, this is trivial. Is that okay? So we obtained, the challenge is, so we proved in particular, once we proved the two sides, we proved that 1 and 2 on the analytic side is equivalent to 1 and 2 on the arithmetic side. So the little challenge is prove that directly without going through A and B. So little challenge. So on the analytic side, you have 1 and 2, and show that this is equivalent to the arithmetic side, 1 and 2. Okay. Now, let me show you that what is on the board here is related, it's a particular case of the general problem, which I had said is deep here. It's still on the board. I should not say question, I should say problem here. So let me write relation to deep problem. Let us consider, so I have to produce for you a connection, a flat connection, and then I have to tell you which is constructed out of A and B, and then I want to relate it to a connection with finite monodromy, so I say deep problem for finite monodromy. Okay. So what do we need? We need an X, a manifold, and we need a connection, given A and B, or given A, which determines B. So X is going to be GM. So we say X is GM. So what is that? That's a multiplicative group, or if you like, if you take the complex points, and this is just C minus 0. Okay? And let us fix a parameter, what do we want? T. Okay? So we have to produce, so that's number one. I say the X which is going to be, the X which is going to do it, which relates to our problem here, is this one, and now you want a connection. And the connection is really dummy. That's the easiest possible connection which we can write down. We need a vector bundle and a connection, okay, on the vector bundle. Now the vector bundle, I take the trivial vector bundle. So I take E to be O. the sheaf of regular functions, which is, if I look at the global section of O, what is that? This is, if you like, gamma XO. This is, so let's say we are over C, TT inverse. Is that okay? And now I want, there's one thing I didn't do because it's not a course, because I don't have the time to develop the whole theory. How, because of the Leibniz formula, you remember the Leibniz rule. To know the connection, it's enough to know the value of a generating section of E. Because I take one section of E which is non-zero, and then any other section is this section multiplied by a function, and then the Leibniz rule is telling me how the connection is built once I know the value on the non-vanishing section, right? So I just have to give you nabla of 1 that defines the connection. And then, so let us write it. This is B dt over T. Okay? So B dt over T times 1, the section 1, okay? Tensor 1. And this is clearly integrable because there are no two forms on a dimension 1 manifold. So it's integrable. Okay, so that's our B, which is here. And what is A here? It's exponential 2 pi IB. This A is precisely the monodromy of this connection, because what is the solution of this? So let me write briefly here. What time is it? Oh boy, 1 second. I have to speed up 1 second. Okay, what is the monodromy here? We want a representation. So first, help me. What is topological fundamental group? Let's say we base it in 1, because we have to base it somewhere. What is a fundamental group of C minus 0? There is only one loop. This is Z. Is that okay? So we have, so let us write here, we have 0 here, we have, let's say 1. We have to fix a base point. Doesn't really matter where it is, so we take 1 here. And then we have one generator, it goes 1 time here, okay? And how is a monodromy constructed? We take the sheaf here, so we take a regular function, okay? And we take its value at 1. So, and now the regular function on the sheaf, I take a solution, I mean the kernel of the connection. So I'm looking, what is the kernel of the connection here? Let us compute it. So we have a function, let's say f. And this is a nabla of f. So how do we compute this? This is df times 1 plus fb dt over t. And we want the 0 of that. So we say 0. And what is that? This is df over f. So I'm not so good at computing, so I apologize if I write nonsense, but I mean, roughly it's correct. And then we integrate. And then, this is what we obtain here. F equals exponential minus 2 pi square root of minus 1 times b times a constant. Okay? And now, as we look at this solution, we move it, we move it, we move it, we move it, we make one loop. This constant is going to be replaced by bt. I'm sorry. And then the monodromy is precisely gamma goes to exponential 2 pi I square root of minus 1 times b, which is precisely our A. Okay? So this justification of what I had written before. And now you please listen to me. Now, what is the condition for this connection to be trivialized étal cover? So what are the finite étal covers of the punctured? Exactly. We know the Galois group, we know the fundamental group, and we take profinite completion. So you are completely right. They are all like this. So GM, tac, GM. So let me denote, so down the board, our parameter was T here. So up the board, let me, S is maybe not so lucky, let me say Z. Is that okay? So any finite étal cover, here we know it, this is Z maps to T equals Z to power N for some N. That means we know because the topological fundamental group is Z. So according to what I told you before by the Riemann existence theorem, a finite étal cover has to be given by a finite quotient of Z, and they are all of the type Z mod N. So there is no choice here. So very good. So to say that to say that it trivializes, it means what? It means that this function becomes trivial here. Said differently, so there are various ways to say. You can say that this function here has to be algebraic over the field C of t. This is one way to say. Okay, so algebraic. So let me write this function f, algebraic. Or equivalently, we know what are the algebraic functions because of this. Equivalently, B is in Q. Okay? So now let us look at what we have done here. So notice the analytic side of our discussion, of our Kronecker discussion, was telling us that A is a root of unity if and only if something happens, and root of unity is precisely, A is a root of unity, okay? And this is precisely saying that our connection trivializes over finite étal cover. And now look at the right-hand side of the board. This is precisely equivalent to B equals Q, and now we analyze what is written. And what is written here? So what is B? So you remember we were saying, so now the first condition we have to say, B is in a number field. So our first condition, B lies in a number field. But this is saying what? In geometric terms. You know, our GM is a variety, it's even a scheme over spec Z. I mean, it's not only a complex variety, it's a scheme over spec Z, it's a scheme over Q. So it means our connection, our bundle of connection, which are data of algebraic geometry, are defined over a number field, okay? So let me just write here, IE. Our inner is defined, over K, which is a number field. So this was the first condition. Is that okay? The second condition was the one I don't want to prove, you can prove yourself. It's telling us that mod P for almost all prime of K, mod P, B isn't the prime field. But what is the characterization of a number being in the prime field in a finite field? It fulfills an equation which is? Yeah, so tell me more precisely. Yes, minus B is, so this is, you are completely right. This is BP minus P. But P means really in Z, I mean a prime number, not in your Dedekind ring. So P, it's a prime in Z, okay? It's 0 mod. Is that okay? For almost all P. So let me write. So I abbreviate here for almost all P. Now I give you that just as the definition, and I close the session with this definition. And b to the power p minus let me write like this, b to the power p minus b mod German p, okay, is the p curvature of inabla mod p. You don't know what is a p curvature. I just say this is a definition in this case. So we obtain the following theorem, which we computed together, except that we didn't redo Kronecker. So let me write and then make a concluding word before the second lecture. So we obtain it's an elegant way to say Kronecker, obtain the following thing, the following theorem on our variety, which was GM, with our differential equation, which I don't rewrite. Then has finite monodromy. If and only if the p curvature mod p for almost all p is vanishing. Of course, a general definition will come later. P curvature is equal to 0 for almost all p. And this is a particular case of the so-called very profound Grothendieck's p curvature conjecture. Now, so I think it's very nice, okay? But there's one thing I didn't do, is that I had this challenge, show 1-2 analytic is equivalent to 1-2 arithmetic, but here the conjecture is only, so to speak, on 1-2 arithmetic. So the general conjecture will be analog, so to speak, to the 1-2 arithmetic. But what is true is that the 1-2 analytic we had, how do we characterize that A is a root of unity? This characterization is easy, because essentially the keyword which is behind, you can think by yourself, but what is the keyword which is behind? We are looking at I don't do the proof completely, but saying that we have an algebraic, it has to be an algebraic integer, it means that we will, at the end, we will be in a group which is discrete, because the roots of unity is not only numbers, algebraic integers, they build a group, okay? So we are looking at the part of the group which is discrete, one has to show it's true, and in addition, the norm has to be 1, that means it has to be compact. So what is behind is classical topology, is that we are looking at a subgroup of the roots of unity, which is precisely discrete and compact, so it has to be finite. Okay, so this is classical topology. While on the, a very important instance of the p curvature conjecture, which we know, and which is basically the only instance we really understand, is precisely because we are in the position to apply a similar theorem. That at the end, we end up with a group which is discrete and compact, and consequently it's finite, and this is a monodromy group. So this kind of argument is much easier than the one which is proposed by Grothendieck in the p curvature conjecture, which wants to characterize not on the side of the monodromy, But on the side of the connection, wants to characterize finiteness on the side of the connection. And then, so then we do arithmetic geometry, so this is harder. And even at the level of Kronecker, it's a bit harder to prove the arithmetic side than it is to prove the analytic side. So I think if one had, just for fun, a direct way in this classical case for numbers, to go from one to the other without going to the final answer, that might shed some light on the general problem. But I stop here. So I didn't present the whole program as I intended to do. So tomorrow, so one thing is how to recognize finite connections and in general Gauss-Vannin connection, and I will define the P curvature and I will discuss that. And another important point, which is not in the abstract which I had written, because at the time I wrote the abstract, I wasn't sure we could prove the theorem, but now I know we can prove it, so I will add it up because it's part of a global program here. The other part concerns, here, this concerns connections of geometric origin, how to recognize the property in characteristic 0 via some properties in characteristic P. And then there's another program which is now due to Simpson. I mean, not a program, but a problem, a conjecture, is how to recognize he is asking, among the connection which are of geometric origin, there are those which have an extra property which are called rigid. So rigidity in mathematics, in pure math, is a very important concept which shows up in representation theory, it shows up in algebraic geometry, it shows up in arithmetic geometry, and here it's an instance. So we are looking at rigid connections, and I will explain what it is. So I have to say something on Simpson for this and Higgs bundles, but very briefly. And then his conjecture relates rigid connections. He claims that rigid connections are of geometric origin. So it has lots of sub-problems and sub-conjectures, and I will mention one, and I will come back to characteristic P. So that's roughly the program. So thank you very much.